When computing limits of trigonometric functions, also known as trigonometric limits, there are two facts that we need to remember, at least for now. First, we have the limit as x goes to 0 of sine x over x equals 1, and the second one is limit as x goes to 0 of the quantity cosx minus 1 over x equals 0. And I know it's no fun memorizing things, especially when we don't know where they came from. So let's talk a little bit about where these things come from. And really all of this hinges on this first one, the limit as x goes to 0 of sine x over x equals 1. So just to provide a little bit of visual context, let's take a look at this thing in Desmos and see if we can get a feel for at least believing that is true. Okay, so here I've graphed sine x over x, and you can see that as we go out towards infinity and negative infinity, that x in the denominator is going to pull this thing down to 0. But as we go in towards 1, as x goes in towards 0, we can at least see very clearly, at least visually, that the function starts approaching 1. So we can be at least convinced that it's probably true, but this is by no means a proof. It's just something that allows us to justify thinking, okay, this is probably true at least, that's the limit as x goes to 0 of sine x over x equals 1. Now, I'm not going to prove this here, and the reason for that is the proof for this using straight up limit and geometric arguments is quite lengthy and quite involved. And once we develop something called L'Hopital's rule, we'll be able to compute this thing in literally about 1 to 2 seconds. So what we need to do is prove L'Hopital's rule, which we'll get to later in this course. So I'm going to hold off until we get L'Hopital's rule and leave the proof out. But just a glance at what this proof looks like if you want to do it without L'Hopital's rule, let's check that out. So we're just trying to prove the sine version of this, and you can see, so here's the proof starting down here, and we're using various triangles and sectors and all of that stuff, areas of sectors. So we got areas of triangles, areas of sectors. So it's a really deep geometric trig proof, which I recommend that you go through. It can be found in any calc textbook, including ours. But what I like about L'Hopital's rule is that it uses calculus to prove it, and then we can avoid using all this trig and geometry and get a very nice kind of higher level calculus proof that avoids all of this talk of areas and sectors and all that. So look at, we got the squeeze theorem in there and everything. So it's a great proof. Read through it on your own if you're interested. But for us, for now, let's just accept this as a fact and move on to the next so-called fact, which we can actually prove. So we'll accept the first one as fact, and then we'll set out to prove the limit as x goes to 0 of cosx minus 1 over x equals 0. Okay, so proof of the second one. Sticking with the calculus in this one, we have the limit. In this case, as x goes to 0 of cosx minus, make that cosx minus 1 all over x. Let's hit this with the conjugate here of cosx minus 1. So cos x plus 1 over cos x plus 1. Alright, that's giving us the limit as x goes to 0. Well, we hit it with the conjugate here. Foil those together. We have cos squared x minus 1 over x times the quantity cos x plus 1. Now, we can use a trig identity here. Can you spot it? It has to do with this cos squared x minus 1. Remember, the Pythagorean identity is telling us that sine squared x plus cos squared x equals 1. So sine squared x is 1 minus cos squared x. So what that tells me is then cos squared x minus 1 all must be, if we put a minus on the front of sine, we can put a minus in the front of all that, giving us cos squared x minus 1. So all of that on the top there, so we have the limit as x goes to 0 still. You got to keep writing that until you actually evaluate the limit. All that on the top becomes replaced with negative sine squared x. All over, the bottom still hanging out, x times cos x plus 1. Now, since this is all multiplication happening in the numerator and the denominator here, we can break that up. So we have the limit as x goes to 0 of, how about negative sine x over x times, and then we'll bring the other sine x here to the other side. So times sine x over cos x plus 1. Now we know from this assumption, so here's the problem, is that we're relying on this other fact that we've just accepted as fact for now, and again we'll go back and prove it with L'Hopital's rule, but for now we know that this is 1, or we're at least accepting on faith that this is 1. So now we're just looking at the second limit. Well, if we evaluate the second limit, what we're left with is limit as x goes to 0 of sine x over cos x plus 1. Well, plugging that in, we just get 0 over 1 plus 1, which is 0. Right? So we did all this, we got 1 here, and then this last bit evaluated out to 0. Which completes our proof. Boop. Proof box there. So if we assume that this first one is true, we can fairly quickly get the second one. So set those to memory because they'll be super useful throughout the rest of Calc 1 and even into Calc 2 and 3.